Okay, this is example 2 of finding a difference quotient. This is the definition of a difference quotient, which should already be in your notes from example 1. And again, the steps to find a difference quotient, which should already be in your notes. I've got a very simple problem here for example 2. I've chose its simplicity because I want to prove a point when we're done finding the difference quotient. So I'm going to come back to the definition of difference quotient at the end. But for right now, I'm just going to set aside this. We'll talk about it again in a few minutes. So step A, the first step to find the difference quotient is to find f of x plus h. So to find f of x plus h, I'm going to take the expression, the algebraic expression, for f of x, and I'm going to substitute x plus h in where x is. So instead of x, I'm going to write x plus h, and then bring down this 1 that's included with the function. And again, as I've said, this is a simple problem. There's no multiply to do. There's no like terms to combine. Right here, we've got the expression already in simplest form. So I'm ready to move on to step B. Step B is to subtract f of x from f of x plus h. So here's how I write that. F of x plus h, subtract f of x. Okay. And I already know what f of x plus h is. I found it in step A. So for f of x plus h, I'm bringing down what I found in step 1, or step A. And now I'm going to subtract f of x. Well, f of x is equal to x plus 1. I'm going to include that in parentheses because I'm going to have to remember to distribute that subtraction across both terms of that polynomial. And that's what I'm going to do in the next step. I'm going to distribute that negative. I'm going to bring down the part that's already simplified.
Logan, please come to the main office. Logan.
I'm going to distribute the negative to both of these two terms. So I've got negative x and negative 1. All right, and now I have like terms that I can combine. So x and negative x are like terms, they cancel. And 1 and negative 1 are like terms that cancel. So what's left is just h. So f of x plus h minus f of x is equal to h. That's step B. Step C is to divide all of that by h. We have f of x plus h minus f of x divided by h equals, well, f of x plus h minus f of x is h. We already found that in step B. So I'm just going to rewrite this here. I'm going to divide that by h. Okay? And so finally, h divided by h is 1. So my difference quotient, f of x plus h minus f of x divided by h is 1 for this problem. Now, I want to talk about what does it mean to be a difference quotient. So back in the definition, we said that a difference quotient is a rate of change of a function over an interval. Now the interval is h. So depending upon where on a particular curve or graph of a function, the left and right bound would be able to give you the length of h. That's besides the point for what I want to make right now. The thing is that we learned about rate of change in Algebra 1 when we were talking about linear equations. In Algebra 1, for a linear graph, the rate of change was equal to the slope. Now, for a nonlinear graph, that's going to tell you that the rate is not constant. The rate is going to change depending upon the interval. And so, looking back at example 1, the more complicated one you've already looked at, you've got a formula for the difference quotient, for the rate of change over the interval, because depending upon where you are on the curve, the rate of change will change. This is not a linear equation, so the rate of change is not constant. In the example we just did, f of x equals x plus 1, this is a linear equation. So it's constant, the rate of change, and the rate of change is the slope. Since the slope is 1, the difference quotient is 1. Okay? So to sum all of that up, if the equation is linear, the slope is the same as the rate of change. Okay, that's it for example 2. Please watch example 3. I'm going to record that next.